All right. Good day, everyone. My name is Ari Hakimian. I'm an application scientist here at C-Therm Technologies. Today, we'll be going through our webinar presentation focused on the accelerated thermal conductivity testing of thermal interface materials. Throughout the session, we'll give a little bit of some background on TIMs in general, certain considerations therein, but really focusing in on the thermal conductivity testing, specifically using C-Therm's transient class of methods. That being said, we'll jump right into it with a little bit of an introduction on C-Therm for those of you who may be new or haven't had much experience with us in the past. Really just a little bit about us. Really our goal is simplifying thermal conductivity testing for the materials of tomorrow. And again, this is done strictly through the use of transient-based thermal conductivity methods, which of course we'll be going into in detail throughout the session here today. Mainly, this will be highlighting C-Therm's Trident platform, which we can see on screen here. If you were here for the first few minutes of that intro video, kind of describe the three different methods that are available. But just to go over those, there is 3 sensors. It's a modular system. On the far right, you can see C-Therm's patented MTPS, or Modified Transient Plane Source. This is one that we'll be featuring quite heavily throughout today's session with some different examples and case studies using the MTPS method. The other 2, I'll just mention them just so you're all aware. The one in the middle there, the needle style sensor, that is called the transient line source, or TLS. And then the one on the far left, that is the more traditional transient plane source, or flex TPS. And again, my colleague Jacob will be putting links to different things that I mentioned here as we go, and we see that first one there of the Trident platform. So please feel free to check that out if you'd like to learn more. And I guess really the reason behind Trident, again, is it gives you options. Really, that's kind of the idea behind the system, modular in nature. Because really, a lot of groups you may be stuck with working with one specific instrument or one specific type of sensor that may work really great for one type of material, but may not translate well to others. And of course, especially in today's research, different labs, you're a lot of times dealing with a multitude of materials, ranging properties, formats, and things like this. So really the embodiment of this phrase here, when all you have is a hammer, everything looks like a nail, kind of with the idea of trying to make one method work for everything, when that might not always be the best way forward. So with Trident, again, giving you those different options to help tackle the challenge at hand with the best tool for the job. Now with that, of course, different methods, different options available, trying to figure out which one is the best option for you. We've authored a method selection guide in conjunction with some different researchers. This is a free available download that you can take advantage of. It's available on our website. Details all of the Trident platform, transient techniques, as well as some other options, different techniques out there, such as laser flash, other steady state techniques, which again, not really focus for us here today, but of course, it is good to know about those, the benefits and advantages and disadvantages of the different options that you have available. So definitely feel free to check that out. And lastly, just before we jump into the main content here, just a little client testimonial. It's always nice to just hear what the client or our customers and clients are saying. This one here from Dr. Samuel Plunkett. His research was focusing on battery technology, specifically thermal management, using phase change polymer composites. Just commenting that the Trident instrument is great. They're able to directly look at the thermal conductivity quickly of their phase change materials, which again are used for these lithium-ion battery packs. Talking about there's no special coatings needed, and coming in at, of course, a cheaper price point compared to some of the other traditional options, such as the laser flash, which I believe they were potentially investigating. So calling it a triple win. So always good to have some nice positive feedback from our customers there. Now, so that's again a little bit of background from us at C-Therm. Now we're going to kind of go into the bulk of our session here today, which is again around characterization of TIMs, thermal interface materials. So we'll start out just a really quick introduction. Those that may be new to this application space, or just of course need a little refresher. Thermal interface materials are essentially designed to fill those air gaps, those voids that will be present between surfaces of typically a heat generating electrical component and a heat sink. So of course, these TIMs help to improve the heat transfer, lowering the thermal resistance, and of course, improving overall performance. Now, those air gaps that are formed, these are really due to those very tiny, very small surface imperfections that are formed between those components at the microscopic level. So if you zoom in at what may look to be two flat surfaces, in reality, there's going to be all these little chasms and void spaces present there. So again, these TIM materials are brought into play to help bridge that gap. Some common TIM materials used, and some that we'll talk about here today, include epoxies, silicones, urethanes, acrylates, different chemistries involved here, but kind of some different common examples there. And the other note, and this is something we'll get into as well, is with a variety of fillers. So a lot of the time as these materials are being modified, just the base matrix is being filled with certain materials. In this application space, typically high thermally conductive materials to help further increase performance and heat dissipation of those TIM samples. Now, within these different thermal interface materials, there are also quite a range of different types. So, I have some examples on screen, but these can include things like pastes, adhesive materials, gap fillers, phase change materials, gap pads, tapes as well. These all carry different benefits, and can really be applied depending on the application. So for example, pastes, top left there, you create a very thin bond line and they're non-curing, which, this is typically what you'll see if groups have ever, you've ever gotten to, building an electronic system or you're putting a computer together, putting thermal paste between, let's say your CPU and your cooler, typically use a paste there. And then everything is mounted together through additional mechanical mechanisms. But, for example, certain systems may need some additional mechanical strength there to help keep things together. So that's where perhaps an adhesive or a tape TIM would come into play, because it also not only provides that bond line benefit, but it provides some mechanical strength and securing there. Again, there's a range of different options here, and we'll be taking a look at a few of these different types and how you go about testing those as we go through the session here today. Now, in all cases, typically these samples, the base material are polymeric in nature. So, before we get too deep into it, really just going over some background information on, how heat transfers within a polymer. This can, generally be described through energy transformation of phonons, these lattice vibrations across the polymer matrix. We can see here that the thermal conductivity, or denoted K, is proportional to CVL. So C is the volumetric heat capacity of the material, V is the speed of sound in material, and L is the mean free path of phonon transfer. Typically, as the mean free path increases, this is a lot of the time what is done to help better organize these systems by improving that path of heat transfer, so will the thermal conductivity. So a lot of the times, depending on the chemistry, polymer chemistry that's involved, generally speaking, the more disorganized that base structure, the less crystalline, the lower is the available path for that phonon transfer. So as you get into more crystalline structure, better organized polymer chains, that will generally increase your effective heat transfer performance. But of course, like I mentioned, there is also the aspect of adding these conductive fillers to your material. Some ones that we have on screen, some common ones used, alumina, copper, boron nitride, various forms of carbon, graphene materials. If you're looking into the research, into literature, these are some common materials used. But of course, there are certain things to consider here. Where these are being introduced into these electronic components a lot of the times. For example, copper is a well-known metal with exceptionally high thermal conductivity. However, it's also electrically conductive, so it may not be the best option as a filler for certain electronic components where you need that dielectric aspect. So again, different things to consider with these different filler materials as they relate to the application that you're looking to use them in. Now, of course, once they are added into the your polymer matrix or your material, again, what they do is they necessitatively improve the heat transfer path for that material. So, in the image on the left, you don't have any filler, disorganized polymer chain. What you'll get is that phonon scattering, of course, leading to a poor thermal conduction, compared to what we see on the right, which of course you have that filler network forming, leading to a improved heat transfer path and thus improved thermal conduction of that sample. Now, when we're talking about TIM and TIMs and really quantifying performance there, I've kind of mentioned thermal conductivity a few times. This is a metric that many groups will focus on. It's essentially a measure of a material's ability to conduct heat. You can see it's expressed in units of watts per meter Kelvin. Essentially, it's looking at the amount of heat that flows per unit time through a unit area with a temperature gradient of 1 degree per unit distance. So again, really a measure of how well that heat is transferring through the bulk sample. This is also an intrinsic material property. It does not change with respect to whether the sample is the different shapes of the sample, the size, what have you. It is true to that material. The other property and what some groups will look at, and if you look at the technical data sheets on these different TIMs, you may see both of these, or perhaps in some cases only one or the other reference, but thermal impedance, this is another metric that is used to quantify TIM materials. And thermal impedance, this is a measure of the sum of a few things. First off, the thermal resistance of the material itself, and secondly, all thermal contact resistances of that material. So thermal resistance, first off, this is a thickness dependent property. It's related to thermal conductivity. So if you have the thermal conductivity of your material and you know the thickness, thermal resistance can thus be calculated or determined. But then there's also the thermal contact resistance, and this is related to the surface contact made between the material in question and the other interfaces it is in contact with. So not only are you looking at the bulk property through the thickness of the sample, but also at the exterior edge portions and how they're making contact with the rest of the system. So both of these can be used, and a lot of the time they're used in conjunction. So I just want to take a note on measuring each of them, and I'll just start with the thermal impedance. This won't be the focus of our session here today, but I did want to just touch on this very briefly. So when you're measuring thermal impedance, typically this is done using a TIM tester, conforms to ASTM D5470. We can see a kind of a schematic diagram. This was taken from the ASTM standard. You can see on the right. It's classified as a steady state technique. One of the things to note about TIM testers, if you have experience with them, then you know they're highly influenced by the applied force and the sample thickness that's resulting from during the testing. So these are two kind of factors that need to be kind of controlled and well understood during the measurement. And the results can be used to calculate the apparent thermal conductivity. This is the verbiage that's kind of pulled from the standard there. Again, you're taking a one measurement and then converting it, so it's not, of course, a direct measurement of thermal conductivity, but it does provide a means of getting you that value. There are certain things to consider, of course, then certain biases that may be introduced. But one of the things just that you find interesting is going through the standard. They do not provide a precision or bias statement for this standard test method. So I guess when you're looking through that, trying to kind of figure out like where your error may lie, be a little more challenging with certain techniques compared to others. Now, when we're looking at measuring thermal conductivity, again, there are a range of different options here. Kind of breaking it down in a table, you see steady state methods on the left. Again, not really getting into those, but if you think of your traditional guarded hot plates, heat flow meter style measurements, again, they have certain advantages with kind of certain materials. A lot of times in insulation type materials, you'll see a lot of reference to that type of testing. But for us here today, and we're really looking at these accelerated test methods, that's where we're really going to focus in on the transient class of techniques. And specifically the three that are kind of highlighted in that blue square, which are the three that, again, are available on the Trident platform. So why transient? Why do we focus on transient methods? Few reasons here, kind of going through them, providing you with a means of representative testing. So these methods, these different sensors, quite easily configurable in a range of different test conditions, so whether that's a controlled atmosphere, specific temperature, pressurized environments, testing under specific force loads. They do provide you with different accessories, different capabilities to place these sensors in those environments and really get you the most accurate and representative test data for your materials. Of course, they're faster than your traditional steady state options. Just inherent to how these methods work, they will always be faster than any steady state counterpart. Measurements can be taken in a matter of seconds, which is, of course, quite significantly faster than the steady state options. And then lastly, a note, generally greater flexibility on samples. So that's not only the type of samples, but the size as well. Many of those steady state techniques require very specific sample geometries, certain sizes that need to be met. And if you're in the R&D phase of material development, sometimes it's not always feasible to create these kind of large materials or large samples needed for those type of measurements. So with these transient techniques, you can get away with samples that are a few millimeters in diameter. They can be solid, liquid, testing powders, pastes, quite flexible in that regard. So of the transient techniques that are available on Trident, again, we're going to be focusing in on the MTPS. So just to give you a little bit of background on this method, few points. It's a single-sided sensor that has some unique advantages with how the sensor can be used for certain types of measurements, not only just kind of getting thermal conductivity data, but certain aspects such as thermal mapping, quantification of different surface, like side-to-side differences, and I have some examples of that coming up. It reports out thermal conductivity and effusivity, conforms to ASTM D7984, which is specified to the effusivity measurement there. It is the fastest of all the Trident methods. So of the three, the MTPS will provide measurements within 1 to 3 seconds, depending on the calibration that is being used, the type of material that you're testing. And it is also, again, really the most versatile of the three. So it is the one that can test kind of the widest range of samples, so solids, liquids, powders, pastes, adaptable for high pressure, broad temperature range, things like this. So I'll give a little bit of a high level overview on the principles of operation of the MTPS. Again, if this is new to you, just to give you a very kind of high level understanding of how the sensor works. So you'll see in that top left image there, there's a spiral heating element. So this is essentially the active area on the top side of the sensor. This is what's used to deliver the heat pulse for the measurement. So this will heat up, and then as that heat pulse is being delivered over that short time period, again, about 1 to 3 seconds, it is simultaneously monitoring the change in temperature that occurs as a function of time. In the image on the right there, you can see kind of an example of two different material types, a foam and a metal. Of course, these materials will respond differently to that increase in temperature that is delivered from the sensor. And based on the rate of change that is observed in the software, so kind of seeing the steeper versus not a steep rise in temperature, that information is fed into the software, and the thermal conductivity, thermal effusivity results are tabulated automatically for you. So with the MTPS, the nice thing is there's no user analysis required. There's not any data adjustment. You don't have to play around with any of that. You simply set up the measurement with the appropriate calibration, run your measurement, and then the results are tabulated for you automatically. The other thing I'll flag with the MTPS, it's kind of noting in that left image there again, the guard ring. So you can see that there, the guard ring goes around the circumference of the sensor itself. Effectively what this does, the guard ring helps to support a one-dimensional heat transfer into your sample. It does so by negating that lateral heat loss from occurring. And effectively what that does and what that means for you during a measurement is that you're always going to have a directionally dependent measurement with that heat pulse traveling normal from the sensor surface into your test sample. So with that being said, I'm actually going to kind of show you a quick little video of an MTPS demo. I kind of did this recording earlier this week. But basically, I'll just show you how quick and easy it is to set up a sample. We'll be looking at a thermal grease, how you take that from kind of sample container, sample vessel onto the sensor, and then how you run your measurement there. So let me just stop sharing here, and I'm going to pull up this video, and I'll kind of talk you through what's happening as it's occurring. So we see the MTPS sensor just kind of laid out in front. That's a liquids and powders cell that we're placing over top of the sensor. This is, of course, can be used to contain these non-solids. The thermal grease you can see there is being ejected from the syringe, filling up, making sure we're covering the active area of the sensor. Just as a note, only needed about 2 milliliters of total volume there. And with that, we're essentially ready to start our measurement. So next, what we'll see is we're going to swap into the Trident software and start our measurement. So kind of looking here, I'm just going to pause the video very briefly, but you can kind of see the layout of the software here. Top left, we see we're working with our MTPS method, kind of our basic information set up on the left. And we are running, I'm just going to let it run one singular measurement here, start over there. There we go. So we're going to initialize the measurement. It's going to take one measurement here, and we'll kind of see what the results look like. But you'll notice there's this initial stabilization period that occurs. So that occurs before that first measurement is actually taken and in between the subsequent measurements of our test set. Once that stability period ends, though, the system will automatically go into the data acquisition stage, and we will see that we'll get some data reported out on screen there. So all in all, from beginning of setting up the sample, getting the system up and running, and starting the test, this first data point here was collected in about a minute and 30 seconds. So we kind of see that, pause this here again. They kind of see on screen, there's that graph, that visual representation of what's going on the left. But again, you as a user, you're never going to have to do any work with that. There's no analysis required. All of your results are simply tabulated for you on the right. So you see thermal conductivity in that first column, thermal effusivity reported right beside it. And then, of course, at the far right, for those that may be interested, you also get a readout of the temperature. So the ambient room temperature that this test was performed is about 25 degrees. But of course, if you did want to do elevated or subambient temperature testing, the MTPS, for example, can be placed inside of a thermal chamber or an oven. You can bring that to whatever temperature point you're interested in, between minus 50 to 200 degrees Celsius, and do your testing from there. So you'll always be able to correlate your conductivity, effusivity data to the temperature at which the test was performed under. So, just wanted to give you that quick rundown there. Again, just showing you, about a minute, just under a minute and a half, you can get your first data point from start to finish. So let me get those slides back up on screen here. So yeah, this kind of going forward here, we'll go through some different examples. On screen, these are just some, examples of some different studies that have been done using the MTPS, kind of looking at a range of different materials, different application spaces. But we do have quite a wide range of publications available for download on our website under our resource section. So, if you did want to look up specific applications, specific material types, how these transient techniques have been used for their analysis, please feel free to check that out. We have a lot of content available there. So, just go through a few example studies. These are some different groups that have focused on the MTPS method for their analysis. Here we're looking at this group was looking at varying graphene nanoplatelet loadings on the effective increase in thermal conductivity, comparing it to a specific model that they had developed. And you can see really, of course, backing up the model with some experimental data is, of course, going to be the best way to make sure everything is lining up as you're expecting. But what you would typically expect to see as you increase the filler loading, they were noting an improved thermal conductivity of their composite compared to the lower filler content, of course. This next example, again, similar idea, group using the MTPS, looking at a range of different composite materials by adding different additives. In this case, they're looking at the synergistic effect of different additives in combination, kind of noting that compared to their base, their highest weight loading increased by 156%. So again, different ways that these sensors have been used, the types of data that you can collect in some of these example studies that you can take a look at. One of the unique aspects, and I mentioned it earlier, is on the thermal mapping and settling detection with the MTPS. Because it is a single-sided sensor with a relatively small active area, it does lend itself quite well to this type of analysis. And anytime you're dealing with a material that's got a filler, so whether it's these TIMs, any composites, really any sample that's going to have a filler inside of it, what you'll sometimes run into is dispersion issues, settling or agglomeration. And these can, of course, lead to non-ideal performances of that end product. So having a way to quantify that is going to be really useful. So we're going to look at two different scenarios here. The first being that surface thermal mapping, assessing that dispersion along the face of a sample. And then we'll look at a second example where we're looking at particle settling. So as it may be settling or sedimenting towards the bottom of the sample as it's curing. In this first kind of example here, what the sample that we're looking at is, this is an epoxy resin. This was filled with a conductive metal nanoparticle and quite visibly non-uniform in its dispersion. But what we're hoping to do here is correlate the measured conductivity value at different locations to that filler concentration. So what we're expecting to see is areas with more filler should result in a higher effective K value. So essentially what was done was measurements were performed at different locations across the surface. So you can kind of see here the test locations kind of representing the MTPS sensor size. So the sample is moved manually to these different spots. You take a measurement. And then what we do at the end is, of course, kind of, just kind of correlate those to the filler location. And what we're seeing is almost, again, like a really good correlation here. Areas with lower filler concentration, such as the top left quadrant there, coming in at about 0.347, related to one of the lowest values, lowest filler in that area. In contrast to, let's say, the top right. So the top right, you can see much more densely filled with that filler material, had a value, or sorry, an effective measurement almost 3 times higher. So as we can see in this example, and as we would expect, very large variation across the surface. This is an example of what you could probably describe as a non-ideal sample. You could kind of just tell that by looking at it. But of course, if the samples that you're working with may be opaque in nature, or that filler isn't visibly detectable, those dispersion issues aren't detectable just by looking at it, then of course the MTPS can kind of do this assessment for you. Now the second example here is looking at settling. So again, in this example, again, the same type of material, an epoxy filled with that conductive resin, conductive metal filler. This was set in a slightly deeper mold, just to try to promote and kind of examine that settling that was occurring here. But again, our goal was to correlate the measured K value to the filler concentration, this time on the different sides of the sample. So we basically took the sensor, measured it on both the top and bottom side. And then as you can see, just from the image, you can almost see that gradient forming where near the top side, there's a little bit more of a clear portion compared to the darker side on the bottom. So, in an ideal sample, you'd hopefully see something what you would have on the left. And in that case, whether you measure the top or the bottom side, your conductivity results should be essentially identical. However, in kind of the case that we're looking at, more of a non-ideal or a bad sample there, what we're expecting to see is that the K2 values, so the K measured on the bottom side, will be larger than that of the top side. And that's exactly what we saw. Basically, what we're showing here is a significant increase or a significant difference in conductivity compared to the top and the bottom side. Again, really resulting from that conductive metal filler really settling out towards the bottom side of the material. So again, the MTPS really provided you that ability to do that side-to-side detection to make sure if you're kind of getting that filler settling to one side or not. This next example we'll take a look at is measuring thermal conductivity under varying force loads. So again, a lot of times if you're looking at these different materials, how they're being spec'd, in the technical data sheets, if you were to test these samples under varying percent compressions or increasing force loads, if it's a soft and compressible material, which many TIMs are, those values can and will change. Typically, you'll see a net increase in thermal conductivity as you increase the applied force. So when you're looking at these spec sheets, it's really important to verify if they are providing information on that, so how the measurement was taken, but also what are the conditions that are being used. Because, of course, if you were just to apply significantly high force load on a sample, you can get away with quite a high reported value. But is that really truly representative of that material in reality? So here, kind of just see some basic example. This was taken on some gap pads, kind of on the top there, kind of quite soft, malleable samples, and quite compressible in nature. But these are basically placed with our CTA compression test accessory. You can kind of see that image there on the left. And we tried some varying force loads and, of course, noticing that net increase in thermal conductivity as you increase the applied force on the sample. So again, just some food for thought there on how you go about setting up these samples, what conditions are being used, and things like this. So when we're looking at these types of filled materials, groups that may be working on perhaps formulation development more on the R&D side of things, one of the things to consider, and we've had some conversation with different groups about this, is monitoring the sedimentation of these fillers that may be occurring in just simply alone in that feedstock material. So we wanted to kind of do a quick little study on this, see how that may play out, kind of maybe in more of an exaggerated manner here. But what we did, we took a two-component silicone resin system and filled it with varying weight loads of alumina filler, so the conductive filler. And we essentially wanted to see that if you have, quote unquote, a nice, fully, evenly dispersed system, if sedimentation was to occur, what type of influence does that have on the measurement? And of course, what does that mean for these feedstock resin systems that may be having these fillers, like as they approach their expiry date, or if they're subjected to varying environmental conditions that may result in some settling or sedimentation occurring. So essentially what we did was take the MTPS sensor and position these test columns on top of it that were filled with these various mixtures. Here we can kind of see what the settling looked like at the end of the measurements. So kind of as that settling process has fully occurred, you kind of see that the alumina powder is, of course, settling out towards the bottom side there. But really, we're just monitoring these measurements were done continuously. So starting with just a control sample, the kind of the base resin came in at about 0.157 watts per meter Kelvin. At the 0.5 weight loading, we see that over time, that measurement, as that settling occurs, you kind of start to reach an upper value of about 0.162. And then just kind of following the trend, we looked at the different weight loadings. And of course, as you would expect, not only do the higher weight loadings result in a higher end value, but you can kind of see the trends as that settling is occurring as a function of time. And then finishing off with that highest weight loading there. So again, this idea, just to, again, maybe spark some ideas within your own groups, is if you are working on developing these different formulations, what fillers are being used, things like this, the chemistry is involved just to kind of tailor and fine tune how these products will perform as they age or go through these different changes. Now, of course, in these kind of well-formulated systems, there are stabilizing agents, things that help reduce the sedimentation effects, reduce agglomeration, and things like this. But of course, over time, this is a process that will inevitably occur during the inside these systems. So just kind of getting close to the end here, but as some conclusions, just kind of what we've talked about here today so far. Thermal conductivity is often seen as a key performance metric for these tin materials. Testing with transient solutions is going to be faster compared to your traditional steady state, and typically offers highly customizable test setups, again, whether that's pressure, temperature, humidity, saturation, things like this. Of the options available on the Trident platform, the MTPS method provides some unique capabilities for some really in-depth characterization, again, looking at thermal mapping, settling, or just purely thermal characterization. The fact that it's a single-sided test method really provides some unique aspects there in how the sensor can be used. C-Therm's Trident system offers you really a unique offering for some benchtop R&D and QA/QC testing. So it really provides you with some unique options there. Now, I will just end on a few notes that some of the work that's being looked at this past year and really going into this year is inline solution for process monitoring. This is something that we're actively working on with some groups in the industry, and just wanted to kind of put it out there if there are groups that may be also interested in learning more about this. Really specifically looking at these filled resin systems. The MTPS sensor is being integrated into certain dispensing equipment, these different systems there. We've had, the MTPS being integrated inline in other application spaces, other sectors in the past. But again, this is really an attempt to work before the samples are being dispensed out or kind of formulated. So as they're being mixed together, kind of as they're kind of staying in these systems, is there a way to avoid that QA/QC failure downstream before it even happens? So really just wanted to provide that out there to certain groups. If you are interested, you kind of want to talk to us more about inline monitoring using C-Therm's thermal sensors, definitely please feel free to reach out for that. So all that being said, I'd just like to say, thank you for your attention here today. Again, you can kind of see my contact info on screen, my email. Feel free to reach out on LinkedIn. I've had some nice conversations with folks kind of offline after these sessions. So if you did have any specific technical questions, definitely feel free to reach out. I'm happy to continue those. As I mentioned, our website does have a range of resources available. Past webinars, tech library with different publications, things like this are all available there for free. I will make a note that we are partnered with Rigaku Thermal Analysis in North America. So we've really taken a lot of time today to talk about thermal conductivity, a little bit on thermal impedance, but Rigaku really focuses specifically on DSC, STA, and TMA systems. So we represent them in North America, and this can be another piece of the puzzle. Of course, one property may not be the be-all end-all for the materials that you're working with. You want to kind of have a really nice 360 view of how that works. So again, really recommend the Rigaku options. Again, these are some great tools out there, and they offer a unique capability with the sample observation. So a lot of these DSC systems in industry, sure, you can get nice data curves, but you can't really see what's going on, and sometimes interpreting that data can be a little confusing. With the Rigaku lines, they do provide you with sample observations. So you can actually see what's occurring with the sample as the measurement is occurring. I actually have a quick video I'll just share for you of those that may be interested in this. It's really kind of a unique concept on how these systems work. But here we're just looking at a TG measurement of a PET sample. So you can see as that screening is occurring on the left, you can kind of map out and correlate what's occurring on the curve to the actual sample in the live camera image there. So you can see, nothing's really happening now. We're starting to see a slight change there. Of course, the baseline shift. As that continues on going into that thermal profile, once we start to hit some peaks here, this is where we'll start to see some interesting things starting to show up. So you can see really mapping out that initial transition as it approaches that peak, going through that first change there. So we saw that change in the color of the sample. And now as we go even further here, again, kind of seeing this dip that's occurring and then mapping that out to what's going to happen to the sample there. Now we can see that change that occurs. And it's really nice because as you can see, what you're able to do here is not only kind of see the data come through, but also map that out visually to the samples. And there are some times, of course, where kind of you're looking at these data curves, you might even mistake some of these things for noise if you're not, really kind of attuned and accustomed to what's going on. But when you have that visual feedback, you can tell, no, okay, that peak is real. It's related to that change that's occurring in the sample. And it's just really nice to be able to have that visual experience with these types of measurements as well. And then the sample finishes there. So just wanted to share that. We actually have some upcoming webinars. I believe the slide on that. Yeah, so actually next week, specifically going into more in-depth on some of these sample observations and thermal analysis, calorimetry focused webinar. So that will be coming up next week, January 19th. And then later in the month, on the 26th, we have some guest speakers from MS Sleep coming in to talk about the importance of thermal comfort in bedding. So a little bit of a different application space than what we're talking about here today, but again, all revolving around thermal analysis. I'll leave you guys with just a note, follow us on LinkedIn. This is where you'll get all the up-to-date information on new webinars, different blog posts, content pieces. Really going to be the best place to kind of keep in touch with us. If you did want to perhaps take a next measured step, you're interested in maybe getting a little bit of a demo of a system, or kind of taking those steps to get kind of talking about your application, or even if you just want a quick quote, please feel free to reach out. We're happy to assist there. And with that being said, we'll bring the session to an end here. What I'll do, really just stop the recording. This will, of course, be available for those that need to drop off, or if you want to share with any colleagues, that will be available for download and playback. But now we'll go into the Q&A session. So for all of you that may be leaving right now, thank you for joining. It's been a great time speaking to you here today.